is not independent of his friend sending it to him. In fact, that violates the first assumption. So, if you consider a deep learning method, one way that these deep learning methods handle these is by the idea of embeddings. They try to project everything into some dimension, compute these embeddings, and work off of the embeddings. But again, there are many problems in which embeddings do not work. And I'm going to show you some of those. And I'm going to show you some of those cases where modeling the data faithfully is much, much more important. And actually, this is also another open call for an announcement. We have a bunch of PhD positions open on these problems. So if you or any of your people that you know who might be interested, send an email, but please note RBCDSAI seminar follow-up, and then include this. Then we'll be happy to look at it. Okay, so because we need a bunch of people, particularly Professor Vibhav Gogat at UT Dallas, myself, Professor Nick Rousey at UT Dallas, Rishabh Iyer at UT Dallas. We have a bunch of people who are working on similar problems who need good, strong people to work with us. Okay, so that's another open call for PhD. Okay, with that, moving on forward. Once I assign control here. Okay, so I work in this problem called human allied AI. Okay, in human allied AI, the way I see it is the human and the machines are, in some sense, they are friends. Okay, they are allies. They are working together to solve a particular problem. And when we are working together to solve a problem, they don't really have a competition. So nobody is winning, nobody is losing. So why I want to emphasize this all the time is because of this notion of adversarial machine learning, which has taken off for good reasons in the last half a decade or so. But we want to work on problems that where human is an ally for the machine learning agent or whatever AI agent that's running in your system. The goal for me is to say, okay, I have these problem at hand and I have a human to help me. How can I effectively use the human to arrive at a better solution? So think of the optimization function that we wrote yesterday. What did we do? We had a log likelihood plus a complexity penalty. That's my learning objective. So it had a log likelihood and a complexity penalty. What my group does is tries to add another penalty, which is the human input penalty. So human can say something like, I work with, this is again a real problem that I work with. How you've all heard of now, I'm sure, ECMO treatments, right? Even the legendary singer SPB was put on ECMO. ECMO is this system, kind of like ventilator, where you're put on life support. So it'll allow your organs to recover. But the problem with ECMO is that when you put kids on ECMO, it can cause severe injuries. And some kids can die because they are on ECMO. Neurological injuries can happen. So what we are trying to do is figure out which of the kids are at high risk and when should we intervene and what should we do to intervene. And there, if I run a machine learning model, it just builds a bunch of things. But one of the things that it misses all the time is the carbon dioxide level in the brain, which is being measured and which is actually one of the more important indicators. But machine learning being machine learning, what it does, it picks up a bunch of weak signals and builds a robust classifier. So we are getting excellent performance, but that doesn't necessarily translate into an effective treatment, right? So what we want to do is figure out how, but my collaborator, actually she's also from Chennai, Dr. Lakshmi Raman, keeps telling me PCO2, the carbon dioxide level, is extremely important. So what we have done is now figured out a way by which we can use that input and penalize a model that doesn't use PCO2. So you can think of, all of regularization. So you can think of the data, then there is a model regularization, and then there is a domain expert regularization. Okay, and we do this in the context of pretty much everything. If we have time today, in the last 10 minutes, I want to kind of tell you that. But why am I doing this? Because to tell you that machine learning and AI is much, much more than just learning from data. I just wanted to set the context for that. The thing that I'm also very excited and proud is also we working on this idea of collaboratively solving problems. How many of you have heard of Block's World? Have you heard of Block's World? It's very simple. I give you a picture, build that with blocks. You think it's easy. This problem has been going on for 60 years. and we have not solved all the problems. It's not easy. My 6-year-old can do this, but a machine can't do that so easily. What we are trying to do is actually have a human machine interface where the human can give instructions in English. The machine parses it into a formal representation. I'll tease you with what that formal representation is later in the tutorial. And then once you have that formal representation, the system and the human together will figure out what to do sequentially to solve this. So the difference, why am I saying this now? It is because I want you to highlight the fact that the models, the Bayesian models that we talked about yesterday, and the models that we're going to talk about today is not just for an IID type prediction. It's not just to predict, oh, is this a tree or not? Is this person going to have a heart attack or not? But to ask this question, now that we know that there is a high likelihood this person is going to have heart attack, what can we do to mitigate it? Is our mitigation strategy working? Are we approaching it in the right way? Is this a long-term or a short-term benefit that we should be looking at? All these questions together can be answered using these kinds of methodologies. Does that make sense? I mean, I'm just laying the problem for you, the context. So I don't want, yesterday I felt like I did go through a lot, but it was very kind of abstract in terms of like theoretically, yes, but practically, where is it useful? I just want to highlight some of these. Does that make sense? Any questions? Any questions from the online group before I move on? Okay, so we have done a bunch of work in this direction. We have done tractable modeling of multimodal data, large domains, temporal models, sequential decision making. But I'm going to focus on two aspects, which is I have complex relational data, and there is a lot of noise and uncertainty in the data, and I want to work with these two. Okay, so we are going to focus on 5 and 6 today because this is the focus of this tutorial. Relational data and noise and uncertainty. Okay, so with that as our context, let's dive in. Okay, so if you look at modern data science, okay, everybody wants to deeply understand the data. Deeply understand the data. I hope you get the joke. And it's like given a database, I just want to understand it. And the problem is that the data comes in a bunch of formats. And and I'm reading many of these papers and stuff, and oh, deep learning is the only thing that we need. I beg to disagree. You cannot solve the modern data science using one technique. Okay, we need a multitude of disciplines to come together, and I'm looking at only methods inside computer science. Okay, we need philosophers, we need engineers, we need psychologists, we need linguists, we need everyone to solve problems that are there in current world. But even from computer science perspective, it has to be interdisciplinary inside computer science. Okay, so I think that if I'm coming out a data science group from computer science, that's going to involve people in high performance computing, people in security, people doing databases, artificial intelligence, statisticians, applied statistics, computational statistics. So the way I see it is, or most of us see it, particularly the group that we wrote a book called Statistical Relational AI, that's there on the top left. I think you can see that here. And this book, one second, right here. And the primary hypothesis for all of us is that we need many methods to come together. And in this particular talk, I'm going to focus on like 4 of these methods coming together. Databases, uncertainty. Remember, yesterday I had an entire session on just uncertainty. So to fully do this, I need like entire week of half-a-day classes to teach what is there in the book. So I'm just going to focus directly on the combination today, because I'm assuming that many of you would have had some background in databases, some background in other knowledge representation strategies that we can assume. By the way, again, like yesterday, feel free to interrupt me anytime. Online, I prefer if you could just kindly raise your hand and then ask me a question. Okay, so I'll notice and we can go from there. Okay, so but then again, it's not like it's new. It's not like we are the first one to think of it. Many people have thought about this problem. Many people have thought about the combination. So if you just look at learning, you have decision trees, optimization, support vector machines. We made this slide in 2014. Okay, so deep networks was not there back then as popular So if I have to update it, I would say deep networks, deeper networks, deepest networks, deeper networks, and so on and so forth, right? I mean, people are doing crazy things nowadays. There's a lot of work in logic and knowledge representation. Things like resolution, prologue, description logics. There's a lot of work done in the knowledge representation, which is one of the reasons I keep saying philosophy is extremely important when we do many of these things, because we can capture many of these knowledge from how the philosophers generally do it. Probability theory, that's what we focused yesterday. We focused on the third one, right? We did base nets in detail. I didn't quite do Markov networks, but they are basically equivalent for many of the problems that we are looking at least. And then people started putting things together. People started putting logic and learning, and that is exactly 30 years old now, 31 to be precise, the field of inductive logic programming, where people learn logical programs from data. So given data, can I learn a set of logic rules that explain the data? And then people started putting learning and probability together. We saw some yesterday. We saw maximum likelihood estimation, and then I gave you an intuition of how to do expectation maximization. Remember, with hidden data, we talked about filling the missing value with the expectation, and then maximize the likelihood, and use the model again back iteratively and keep doing. And we'll see a couple of examples of that today as well. And then actually one of my favorite papers, and for that case, my favorite researchers, Nils Nilsson, in 1985, put together a combination of logic and probability, which is one of the reasons my first server that I ever bought, I named it as Nils in honor of his name, Nils Nilsson. So he put together logic and probability together to form probabilistic logic. So you have these rules, and rules are, remember, true or false. And basically he said probabilities are essentially things that cut the boundaries of these rules. So it's not true or false, but I'm going to divide it into regions. And then of course that has evolved into a whole bunch of techniques. And so what we are going to see today actually are putting all three together. So we are going away from simple propositional logic, which is essentially just writing individual instances. As from instance level, we move to first order logic, which essentially talks about populations and subpopulation level. So we can say for all students this is the case, rather than, I'm just going to use your name, Arvind, I think, right? And what's yours? Karthik. So rather than have a rule for Arvind separately and Karthik separately and so on, we can write something about the population of students. And then a population of a subclass of students, maybe computer science students versus not computer science students, IITs versus non-IITs. So we can have these different levels of rules. And that is what first order logic allows you to do, okay? And then in propositional, with vectorized representations, the vectors that we talked about, the IIDs and so on and so forth, from those vectorized representations, we can talk about representing them using probability theory. Okay, for logic, for representing things at the logical level, we can represent them using probabilistic logic. And then now we add learning on top of it. You have your deep learning, support vector machines, decision trees, logistic regression, everything here. But what we are going to focus is this area, where my model is going to talk at the level of populations and subpopulations. And I'll give you a bunch of examples. Is the lay of the land clear where we are starting? Okay, so let me just give you an example. As I said yesterday itself, I'm a very bad movie director, right? So I kind of break the suspense. So let's just start with one simple example. Let's say I'm interested in predicting if a person is going to get heart attack. Okay, so the first thing we check is that the person is a male. Remember yesterday also I told you that men are more prone to heart attack, and we know that. Okay, so first you check if this is a man. Great. Now we start diving deep in, and you say, look, if the cholesterol level of this person above the age of 40 is greater than 200. Okay, now this is where things get interesting, right? So once I, as usual, figure this out, so it's kind of like a timeline. Okay, this is when this person is born, this is the age of 40. I'm looking at this entire area and I'm saying, is there a single measurement here where the cholesterol is greater than 200? So you can obviously see it's a made up example. Okay, so don't get a heart attack just looking at these numbers. Okay, it's a made up example, but the power that I want to show you is that this is looking at this entire timeline after 40. Maybe this person lives till 90. I'm an optimist, so let's assume that this person lives till 90. And I'm basically saying is that any point after 40 that it is greater than 200. Now think about how you would write this in a vectorized format. Pretty difficult to do unless you have very smart ways of encoding it. But your SQL database can easily pull this out by using a simple exist command, which is what a logic would do, and that is where I want to show. So basically, if I write this in logic, you will say there exists a level L and age A such that age is greater than 40 and level is greater than 200. It's very simple to write this in logic. So if you have a powerful representation, you can learn that faster. Okay. Now I go down, and this is where it gets interesting. Now I'm not looking at this person alone. I'm looking at, in this graph, the person P, but the father of this person, and whether the father had diabetes. Okay, by the way, the left path is true, the right path is false. So you're looking at this and you're asking, is the father of the person has been diagnosed with diabetes? If it is true, then I'm looking at the BMI of this person, okay, and at the age of 55. So this is age is 55, is the BMI greater than 30? If so, there is a high chance, else low chance, and so on. All these numbers are purely made up, all these examples are purely made up, but what I want to show is the following. It's completely made up. I mean, I would probably be hit here. So it's completely made up, right? So but the point I want to show is that there are two things you have to notice. First is that this aspect, I can look at a timeline of a person and just look at any value in this timeline, and then I can look at a related person. So I can say, is there if this friend's friend is Shah Rukh Khan, then I don't want to talk to him. But anyway, my point is that the friend's friend, you can ask for the relation, relations relation. You can say if I can reach Albert Einstein within 5 co-authors, that's cool. So that's another way, or Tom Mitchell within 3 co-authors. So the point I'm trying to make is that there are things that you can look at about this person that can be different. As another example, one of you might have taken 5 courses, another might have taken 10 courses. Some of you have published, Ravi has published, I don't know, 500 papers, me not so much. And so if you have to put both of us in a single table format, it's not fair. We want to let the data speak for itself, keep the data in its original format, and then you ask for queries accordingly. And that's what we can do here. The thing you have to notice is that I can talk about particular attribute of a person, I can talk about a variable, I can talk about a value. So I can talk about the value at like a tabular level, then I can talk about 2 tables together, and then I can talk about something that is extremely open-ended. And all this is because I use first order logic as my representation. Does that make sense with me? But the table, the tree is easy to learn. And by the way, if you ask me, Sriraam, what are you known for? It is that we have a wonderful package that can learn trees like this in a matter of seconds on many of these problems. This is what we have been building. Okay. So, but then I talk about relations. So what are these relations really? What are these relations, right? So relations are of several types, okay, and really depends on your view of what a relation is. So relation could be things that provide additional correlations or regularization in classic machine learning. So things like the word counts, context, right? So if certain words are present together, then it means something. Like I want to say, what is a faculty web page? Well, if it lists the list of students or courses that the faculty has taught, then maybe it is a faculty web page. That is a relation. Relations are also extensions in some sense for one relation. So things like distance functions, kernel functions, graphs. So those are all capturing these idea of extensions of relations. So remember, relations are very powerful, and I want you to get that. It's not just different tables and how they are related. They can be simple extensions for a relation. Okay, they can be symmetries. Okay, so it can be 2 people who are similar, 2 people that have similar attributes, maybe students together in a one particular problem, right? Or if I'm talking of voting, then particularly this group of voters. If it is sports, then this type of fans. So I can start grouping people together where your individual identity doesn't matter anymore, but it's your property and your property relative to others in that group. So that is another way how relations are used. And then of course hypergraphs, where we can talk about similarity measures, and two people working on a paper, co-authors of a paper, and so on and so forth. And finally, problems that you can use full-fledged relational knowledge that we are doing. So 5, in some sense, the last one subsumes all the other type of relations. And once you have this, then we can compute the other relations from relational databases. Does that make sense? So I just want to ground out what relations are before we move on. Yes, with me?
Excuse me, sir.
Is there any question from the online group? Yes,
Yes,
Samir.
there is a question.
Samir? No, I can't hear you.
Sorry, sir. Can you hear me?
You're muted, I think.
Hello?
Yeah, now we can.
Sir, so these 5 different methods have a combination of encoding as well as representation, but do they give the power of, obviously the difference in what you're saying also has a fundamental variance in the strength and the power of those relations
Right.
based on the
And
probabilities.
what they represent. And what they represent.
So in terms of the visualization context, obviously the more detailed versions, which are just data encoding, don't have great visualization appeal in terms of explainable machine learning or AI.
Exactly. Whereas these last one, which are essentially the form of these Horn clauses that I have here, these are much more explainable, because these are rules. This basically says if to say X is an ancestor of Y, if there is a if X is an ancestor of Z and Z is a parent of Y, then X is an ancestor of Y. So it's a simple logical rule that can be written as if then else statements. And you have things like that, then it's much more explainable. Is it visualizable? That depends on your problem at hand, but it is explainable. Yeah.
Thank you, sir. Thank you.
This question about saying that it is explainable, right? And that's because we actually gave it nice sounding names.
Semantic meanings, yes.
Yeah, but then that means that before you do any explanation with what you are deriving, you need an alphabet or a language which is grounded in semantics that a human already understands before you can start putting these explanations together.
Exactly.
Right?
Exactly.
This is something that is going to be derived completely from data.
I don't think so.
You can't do explanations, right?
You can't do explanations because we want to explain it in terms of the human understanding of the problem. So actually,
yeah.
I kind of pushed that point yesterday and today morning. Like we learn in the presence of humans. So we have to talk to the domain expert, understand a common representation, and we want to be able to explain things in that representation. If it's,
why is it that more people in the community don't talk about this when they talk about explainability?
well, we are still in the hype. Once the hype goes down, they will start with going down this path, I think. We are still in attention is all that you need idea. I mean, it's hard to get attention from the audience, so but we keep still claiming attention is all we need. But once we get that, once we get past that, I think we will get back to this. So it's I mean, we've been here long enough to see that now, right? So there was another hand that I saw. Is there another question from the
Excuse me, sir. Can you hear me?
WebEx?
Can you hear me from the control room?
Yeah.
There is a question on the chat from Govind.
There is a question on the chat. Yeah.
He asked if logic plus probability is
Sorry, I can't hear you very well.
Is it better now?
Little bit better. Yeah.
Okay. Govind has asked that if logic plus probability is somewhere related to fuzzy logic or soft computing.
Yeah. So fuzzy logic, essentially fuzzy logic and probabilistic logic share a lot of things in common. But the fuzzy logic has slightly different semantics on what it means. And I mean, but the idea is the same, that logical rules are either true or false. It's just that, right? It's black or white and nothing else. But probabilistic logic, soft logic, fuzzy logic, these are all essentially looking at softening the rules to make sure that you are not in a 0-1 world anymore. And so many of us like probabilistic logic because of its tight semantics. That like I yesterday gave you the example, you cannot have 1.73 as a probability, even though my student claimed that he did. So that you can. So that's why we like probabilistic logic. But yeah, they are all very related. In fact, if you read the learning methods and things like close to them, they are not very far away from each other. I hope I answered that question. There was another hand that I saw. Is somebody else having a question, or can we move on? Okay, let's move on. But the thing is, right, it's not new. It's not that we started now. I'll just show you the methods that are inside SRL. Okay, I'm just going to not talk for 10 seconds and let this go through this. So this is where it started. Okay, 1990s. Just wanted to show you, this is about 80% of all the models that are out there in the field that combines probability and logic, probability and relations. So it's not new. It's not something that we did in the last 10 years. People have been doing this for about 30 to 40 years now. Okay, but the thing is, at some point, this was one of the mistakes that the community did. Community was interested in building more and more models for representation's sake. Oh, I can represent this that your model cannot do. Oh, I can compare, get this edge condition that you cannot do. I can do these triples that you cannot do. You can only do binary relations. And so what they did was they started building these models for a long time. But about in the last, I would say 10 to 12 years, we kind of gave up on these models, picked any of them at random, and we were focusing most on the learning and inference of that. So we can do this practically. So if somebody asks, like maybe that answers Professor Ravindran's question on why are we not thinking about it, because of the fact that people focused a lot on representation rather than actually using it on the real data. So I used to joke, and it's not a joke, it's actually true. You write the word Bayesian, Markov, probabilistic, stochastic, fuzzy, whatever word you want on one side, and then you say logic, relational, and then on this side you have programs, models, machines, and anything else, language, logic even on this side. Take a cross product. There will be somebody who would have published that. In every instance of that cross product, there would be a paper. And this was a race. People kept fixing one small things from another paper and kept publishing. So these epsilon improvements, but some of these stand on its own. Okay, but we have moved past it, and now we are focusing on learning and inference. But I wanted to give you some idea of what these representations can capture. First is, are we doing directed models versus undirected models? Remember, yesterday we talked about Bayesian networks, and I said, so can somebody tell me what this actually means? A is the parent of B. What are the distributions that we have here? You had two distributions, right? P of A and B given A. Thank you. This is a conditional distribution. So this is a directed model. Okay, an undirected model could instead just have this, and here you have a potential that is on AB, which is basically saying what is the strength of correlation between A and B. And you can take one and convert it to the other. So you can take this and it can be converted to this, and similarly you can take this and convert it into this. So in the directions of whether it's directed or undirected, there were a bunch of papers that worked on directed models versus undirected models. What is the advantage? In some cases this makes sense, in some cases this makes sense. So can somebody say where, let's say, a directed model would make sense? Just give me an idea. We went through a bunch of examples yesterday. Just quote any of those. Yeah, but give me a domain in which, a problem in which it will make sense to have a directed model. Diseases, we talked about it, right? Causes of diseases. Why is a disease caused? clinically. On the other hand, if I have an undirected model, it's spatial relations. You can't say one pixel came before the other. So typically in the beginning stages of this community called UAI, things that involved time and cause and effect were done with directed models. Things that involved space, people used undirected models. That's how we started this area. Okay, the other dimension, okay, maybe I'll give you some examples, and we can do this in the context of statistical relational learning. So this is basically saying for all x, okay, so this is for all, for people who do not know logic, I just want to give you an idea. This is saying for all x, if x authors a paper P and if x is smart, then P is of high quality. Okay, for all x, if x authors a paper P and if x is smart, then P has to be high quality paper. For all, I guess P here, for all P, if the paper is of high quality, it should be accepted. How many of you have submitted papers? Some of you. How many of you has an 100% acceptance rate? Which means in the first attempt, not that every paper of yours you've got somewhere. But we all believe this second rule is false. It's not that it's false. We will soften it and say this is not always the case, and we will have a distribution. In an ideal world, it is most likely going to be accepted. But in this world, who knows? But at least there is a 50% chance of getting accepted if it's high quality. Make sense? So what we have is associated with each of this, you're going to have a probability distribution. Make sense? So if you only look at this in classic CS, we call it logic programs, because these are programs that encode a bunch of logical rules that you can then query. So what can you do? Let's say if a paper gets accepted, I can go back and say that the author is a smart person by using these set of rules. That's why it's called a logic program. I'll start from what I want, what I see, my observation, and then I can make inferences about other aspects of the problem. That's why it's called a logic program. In this thing, it is called a Bayesian logic program because we put probabilities on top of it, essentially following like Bayes rules. So what happens is, given this and a distribution, we'll call it D1 and D2, associated with each of them, essentially this is a conditional distribution. So this is going to give you the second rule that has a distribution which says probability of accepted given high quality, and it's a distribution like what we saw yesterday. It's a table, conditional probability table. Does that make sense? Now what can we do? You give this and you give a set of papers and authors, you can create a giant Bayesian network. Remember all those conditional independencies and all the thing that we talked, you can apply all of them and answer queries. This is called Bayesian logic program. Make sense? Any questions? Okay, so these are called Bayesian logic programs, and as I said, inference is constructed by instantiation of these rules. So if there is a person called Alice and Alice has published a paper P1, then we can basically say based on everything, and let's say you have seen that the paper has been accepted, you can get a distribution over how smart Alice is. These are just two rules, okay? In real world, in real tasks, we'll have like hundreds of rules, and so this network is going to be huge. So how can you efficiently compute the probabilities? That's where the research is. But I just wanted to tease you in terms of what these things can do. Yes, makes sense? Yeah. Many rules. Brilliant question. Thank you. So for people in the online, the question is, in real world, you're going to have many rules, as I said here, right here. And the question is, are the rules written by someone? The answer is the same as yesterday. If the Bayesian network is provided by somebody and then the data is given to you, you learn the parameters. If the Bayesian network is not given, then you do structure learning where you are learning the structure of the model. So here, and this is what our lab is known for, is can we learn these rules also from the data along with the probabilities, which is what I'm going to teach in the hopefully after the break. Okay, great question. Thank you. Exactly. You can think of it like this. Description logics are some way of representing these with probabilities. Yes. Again, we can do the same thing. There is another author, let's say Bob, and then you observe something about Bob. You can query about other things. Okay. The most important thing is you can deal with variable number of objects. Remember, Bob could have written, I guess, 50 papers, but Alice could have 150 papers. And in both cases, we can still use the same model and come up with the distribution. It doesn't matter how many papers each of them write. You don't need a single vector that captures everything, like what we do with typical machine learning methods. You start with a nice table and you use the table to learn on top of it. You don't need that here. Yes? Okay. So the question now becomes a little different. Here there is a nice change. In the first case, we only had P1 being written by Alice, P2 written by Bob. Now what happens if Bob is a co-author of Alice? Then there is another arrow that comes like this, right? Because smart of Bob also contributes to the quality. Make sense? Yeah, very simple. Now here is the problem. One paper could have 3 co-authors, another paper could have 7 co-authors. How do we get them together? You can do what is called as an aggregation. So you can somehow combine the effect of all of them by taking a, what can we do? You gave us ideas yesterday. Average. I can just take the average smartness and then do this. You could also say, is one of them at least smart? Because sometimes, in particularly if it's not a blind review and you have a big name on it, then the paper gets in, because I've always seen people argue just because of that big name. So it depends on many things. So you can have average, you can have max, you can have min, you can have count, you can have any of these aggregators depending on the problem you are looking at. So the other question is, should we even search over the aggregators? And most of the time my answer is that it's going to be too difficult, because you're going to just increase the amount of complexity. It's like searching over the hyperparameters of a deep network. You have some set of values that you can try and hopefully one of them will work. Same thing here. So what we do is we start aggregating things together, and you're basically saying I'm going to aggregate the smartness of Alice and Bob, and then I can put them together. Okay, and as I said, you can use any aggregator, sum, max, min, average, mode, count, and people have done many of these works. How many of you have actually worked with databases, SQL queries and so on? Some of you, at least. This is exactly what you do. You write a SQL query, you say select sum of blah from blah, where blah. And you can do that in logic very easily. Okay. But again, the model that we are saying is in the end acyclic. It's extremely important that it is acyclic. Otherwise, your probabilistic semantics are not guaranteed. Remember the thing I want, and we'll get back to this. Okay. If this is we saw this as joint rule of probability. This is not joint rule. In fact, this is not a distribution. So you cannot say that this joint can be represented like this, and if you have cycles, this is exactly what you get. which is one of the reason a Bayesian network, remember again, is a directed acyclic graph. We went through this yesterday. So what if you want to do that though? What if you want to allow some cycles? There is something called as relational dependency networks or dependency networks, where you can have rules like this. So if so the same two rules, right? So if a paper's author is smart, then the paper is of high quality. If the paper is of high quality, it gets accepted. But now we add another rule. If both X and if X authors, both X and Y are co-authors, so this is co-authorship right here, and X is smart, then Y is also smart. Now this introduces a cycle, because it introduces a smart cycle. Like you can have, if there is a paper, you can get something like, I don't know if I have an example for this. Yeah, right here. What happens is that you can get this cycle right here. Okay. So when people write rules, they don't care about cycles and not cycles, and we cannot ask them to write rules to make sure that it's acyclic. Turns out that some rules that you write, if you have a database, you can actually get still acyclic models. So what do? One thing we can do is we can forget getting perfect semantics and instead just run Gibbs sampling, which is a sampling algorithm, and that we can approximate it. It's called modified ordered Gibbs sampler. You run that Gibbs sampler with very large amounts of data. This particular issue will kind of like not cost a lot in terms of your final probabilities. In fact, if you don't have a short cycle like this, but I have a very long cycle like this, something like this, right? Let's just pretend like this cycle doesn't exist, and you have a very long cycle. Here, this joint distribution that you get out of this Gibbs sampling is very close to the true joint distribution. So you can theoretically show that if you have a very long cycle, it is still okay if you have a cyclic model. But the point I'm trying to make is that sometimes ensuring this cyclicity is going to be very difficult. That's why we allow for rich representations. And many of you should know Pedro Domingos now, right? Yes. Let me see if people know by nodding. Yeah. So he's written this thing called Master Algorithm, and if you get a chance, get that book and read it. It's a nice read, and that book. And by the way, he doesn't give me any commission for saying this. Just FYI. They took a slightly different approach. They are like, you know what, to heck with this cyclicity business. It's just a lot of work. So let's just go for those correlations. Remember, I told you about the Bayes net versus Markov net. So they basically said, let's just go for an undirected model where we talk of correlations. So they had a simpler interpretation where they say, write your logical rules. The first rule says, if X authors a paper and X is smart, then P is of high quality. If paper is of high quality, it gets accepted. If an co-author is smart, then if two people are co-authors, then both of them are either smart or not smart, right? And their smartness are the same. If X authors a paper P, Y authors a paper P, then X and Y are co-authors. Okay. So now all they are saying is, let's take this and now let's pretend that they all have weights. Each rule has a weight. Higher the weight, higher is that probability of the rule being true. So the last rule, which essentially defines what a co-authorship is. If two people are on the same paper, they are a co-author. Okay, now that rule has to be true all the time because that is a definition of what a co-author is. So that's a tautology. So what do? You assign a weight of infinity. Now you look at the other rules. The first rule says, if X is written a paper and X is smart, then paper should be of high quality. Well, that's reasonable. So I'll give it a slightly high weight. On the other hand, its high quality gets accepted. Well, that's not always true. We know that. So what we have done is we have given this a lower weight than the first rule. And then if both authors are co-author, then both of them to have the same level of smartness, also not as highly true. So that has a slightly lower weight. Higher is the weight, higher is the probability of it being true. And actually you can say how true is one rule compared to another. It is a log of the weight ratio. So log of 1.5 by 1.1 is how likely the first rule is true compared to the second. So given this, what you do is you create, random variables where you have co-author of Bob, Alice, Smart and their papers that they wrote, and then you start drawing edges between those based on the instances of the rule, and then you can perform inference on this graph, very similar to the Bayesian network inference. This particular representation, if you have not heard of this first, is called a Markov network or a Markov net. That's called a Bayesian net. This is a Markov net. Make sense with me? Yeah, go for the question, Rajiv. Rajiv, do you have a question? Okay, he says can't unmute. Okay, so
Sir,
maybe, yeah.
hello. Sir, can you am I audible?
Yeah.
Sir, this when you assign these weights, so these weights will come from the domain information, right?
Excellent question. Again, these are learned. Most of the times they are learned from the data. This is like the parameter learning. Instead of calling it parameter learning, you call it weight learning. Yesterday we saw this parameter learning of Bayesian networks using maximum likelihood estimation. You do the exact same idea. You can learn these weights from data.
Okay, sir.
Most of the times, the way, if you have heard of Chris Ray and his system called Snorkel or Tuffy that people are using a lot in the NLP world, essentially they are saying humans will write the rules and the system can automatically learn the weight from data. So these weights can be learned from data, and I'll show you how. The learning is in the second part of the talk, the lecture. Okay. Hidden Markov models are subsumed by many of these methods. You can essentially write that as a rule, and then you basically get a Markov logic network from that. So yeah, they are subsumed. We can do hidden Markov models. I'll have an example for that. You can do dynamic Bayesian networks, Kalman filters. Many of those can be written this way. So more on Markov logic networks a little later. Okay, and then there is also another direction in which there is this idea of proof theoretic versus model theoretic method, where how many of you have heard of context free grammars? Must be a lot of you. No? Okay. There is a version of that called stochastic context free grammars, where you can add probabilities. Context free grammars. That's why we need a faculty here to get the correct answer. We should relook at our CS curriculums. So context free grammars, where you can start writing these, like even like linguistic things, like a sentence consists of a noun phrase and a verb phrase, and then verb phrase consists of this and noun phrase consists of this, and you can keep writing these rules out, and then I give you a sentence. Then you can say, is this sentence subsumed by your grammar? So you can extend that idea, and I say I give you something like this, a set of rules with weights, and I give you two things, maybe a person who's smart but doesn't have a single paper. What is the likelihood that this theory could have generated this data? Can you prove the data from the theory? So those are called proof theoretic methods. Okay, I'm not going into the detail because they are also very related to just doing probabilistic inference, but that's another way that people looked at. And as an example, this was supposed to be an animation that did not work. So let me just at least move this thing around so you can see this. Okay. So you can have things like, I have edges between a gene and a disease, and then some edges between the disease and gene, and then I can have some rules that describe the domain. So if there is a path between xy, if there is an edge between xy, or if there is a path between xy, if there is an edge between x and some other atom z, and there is an edge between z and y, or a path between z and y. Okay, so it's basically defining rules of the domain. Let's say this is just a genetic link domain. Now what I can do is I can give you a question. Maybe I can just give you this particular disease and particular gene, and I ask you this question: what is the probability that there exists a path between them? And you're going to prove that using this notion of prob-log. Prob-log is this idea, this part is logic program, this is probabilities on top of them. Again, I'm not going into the detail, but you can also, the point is that you can simply define distributions on these probabilities using such a model. So what I'm trying to show you is all these different, representations which can do very similar things. Okay, and we'll talk about that. And there are many assumptions. Are they parametric? Are they non-parametric? Remember, non-parametric does not mean 0 parameters. It means they are infinite parameters. So you can actually add parameters as you need to them. And then closed world assumption versus open world assumption. Closed world assumption is what you make in databases. Can anybody tell me what a closed world assumption is? Anybody here? Closed world assumption says whatever you don't observe is not true. If your data doesn't assert anything, then it is not true. Open world assumption says that, well, there could be things that are not true that you still don't observe, like life on other planets. We don't know that yet. Life on other, not other planets, other I guess solar systems, other universes, other galaxies, right? Yes. Closed world assumption is basically saying I don't see the end of Earth, so Earth should be flat. No, I'm just kidding. But the point is that closed world assumption means that whatever you don't observe, you assume it to be false. So when do you prefer one over the other? If you want faster, efficient reasoning, you make a closed world assumption. You want an accurate reasoning, you make an open world assumption. But open world assumption can lead to a lot of complex reasoning that may not work very well in practice. So we all make closed world assumption at some point. Okay. And the thing is that what I want to say about this representation, to just cap it off, is that it spans the whole AI spectrum in some sense. We can do things like topic models, Gaussian processors, reinforcement learning. Actually, Professor Ravindran and I work very close on this idea of relational reinforcement learning. We can do linear equations.
Sorry to interrupt you, sir.
Yeah.
Sir, could you please tell me like how the closed world assumption goes for this this model? Like, say for example.
So for instance, if I ask you this question, right? Let's move back to this example of co-authorships. Okay. So if A and B have not written a paper that you don't observe yet, but A is smart, right? Then to know whether B is smart or not, we only use B's paper that B has written, not A's papers, because that link between A and B is something that we have not observed. We assume that the link is false, so we cannot use the link between A and B. In an open world assumption, you can have a distribution over that link and say, oh, maybe they have written a paper that we have not seen yet.
Sir, is it something similar to that hypothesis framing?
Hypothesis what?
I mean, framing and hypothesis, testing and hypothesis, test of hypothesis.
Well, yeah, this is, well, but we don't, so if you think of it from the hypothesis testing perspective, you don't explicitly test if they are co-authors, because the data cannot give you that. But you maintain a distribution over that. You assume that it could be true.
Okay, something like similarity. Okay, sir.
Yeah, well, that's one way to think about it. Yeah, sure.
Thank you, sir.
And you can have that similarity score propagate.
Okay, thank you,
in open world assumption. Whereas in closed world assumption, you say that it's not true. That's it. They have not written a paper together. So I'm not going to use that fact. Yeah, sure.
So there is a question from chat.
Yes.
Ratchaswamy has asked that the peer reviewing conditions between journals might differ.
Slow down.
The
louder,
peer
please.
review conditions between different journals might differ, right? So like publishing in
yeah, sure.
So
the point is that can be brought out in the rule as well.
So his question is, how best can these qualitative factors be expressed through probabilities expression?
Yeah, I get the question. So let me go back quickly. I have to go back for long. Right here. Okay. The reason I showed this was that you can talk about a relation, you can talk about a specific value. You can talk about a relation, you can specific value or attributes of an object. to extend this to the conference example, here I can say if the conference is an A star conference. Okay, and I can basically, if it's an A star conference, it comes up with a different set of rules. If it's a third tier conference, it has a different set of rules. If it's a predatory journal, it's a different types of rules. The point I'm trying to make is that the use of first order logic as your representation allows you to partially, talk about what the level of conference is. It's actually very easy to write rules like that in these formalisms. Remember, it's easy to write, it's not easy to learn. So that's the two different things. It's pretty easy to write these rules. Can you learn that? That's a different question. You need a lot of domain knowledge, you need a lot of inductive bias. There is no free lunch. So we have to figure out how to learn these rules correctly. Something that we work in our lab, but that learning is not easy. I hope I answered that question. Okay, so with that, we can move a little bit and talk about this. Even in UAI, right? So when we talked about this alphabetic soup, then we thought even inside UAI, there were a lot of things that were built earlier. Okay, and in the end, people kind of narrowed it on in one or two problems, and then worked with those problems. Representations like that, we can just take one or two representations and work with them, even though you have different ways of writing the same thing, because the knowledge is the same. The underlying model captures the same things. Okay, so the same idea can be done for relational models. So if whatever, right? Remember, I wrote this. Let's go back to this example. There is A and B, and then you have these two distributions, P of A and P of B given A, or you could have this potential. Okay, so both of this together can be represented by what is called as a factor graph. In a factor graph, I can have x1 and I can have separate factors. So this FA captures the interaction between x1 and x2. FB can capture a different interaction between x1 and x2, and FC could capture between x2 and x3, and FD could capture only x3's potential. So this could be like a prior over x3, and this could be two different conditionals that you can work with. So what people have done in the probabilistic graphical models community is kind of come up with a representation called a factor graph that kind of unifies all these methods, and most of these methods can be written out like this. And now you can take this the probability essentially as just product of these factors, whatever you are instantiating with. If x1 is 1, then maybe it's FA of x1 1 here, and then FB of 1 here, FC of 1 here, and FD of 1. And you get basically if all three of them are 1, and the final one you get is like this, but this is an unnormalized, so you have to normalize it. Remember, we talked about it yesterday. Essentially, you divide it by the sum of all the other values. So we can do the same thing for the statistical relational models, and this is showing how to do this. So remember, this was the Bayesian network we saw yesterday, something like this. You have x1 and x2, and they are parents of x3. You can write out the joint distribution as the priors, the product of the priors and the product of the conditional. Now you can write this as a factor graph where there is this that captures the prior over x1, this that captures the prior over x2, and this is the conditional of x3 given x1 and x2, and FA is simply this prior, this prior and this prior, and you can capture it very simply. This is a Markov network. I just talked about this. It's a clique. So the clique has one potential. Well, there is actually a direct translation with the same potential being the factor. So the point is that there is an intermediate representation. It's not how you, again, going back to Professor Ravindran's question, I cannot use the factor graph representation. I cannot just present this to the domain expert. It's very hard for the domain expert to understand this, but it's easy for the domain expert to understand this. So these are things like, like compiled code, right? So code that is an intermediate representation. It's not your programming language, but it's a compile level code. Factor graph is like that. Okay, so what we can do is you can have something, we call it boiling down, some other boiling down process that we can do even in these relational models. Instead of having the whatever probabilistic logic program, Bayesian logic program, blah blah blah, you have a factor graph representation. Okay, it's parametric factor graph, and then you can learn and perform inference on these graph. So what I'll do is I'm going to introduce this idea of structured learning, where we are learning these rules and probabilities, and then we'll go from there. So remember, again, yesterday we talked about this parameter learning, where the model is given. So given model, you are only learning the structure, the probabilities or weights, depending on how you represent. Here, given only data. Now, how does the data look? The data is essentially an assignment of values to variables, but they can be partially assigned, and this is where EM comes in. Remember that. So it's a refresher. That's what I'm going to do. So what I'm going to do is I'm going to introduce. Remember, I'm going to refresh what we talked yesterday, and then I'm going to move to this. If the complete data is given, then what do? Maximum likelihood estimation. What is maximum likelihood estimation? We talked about it. We had an example, and we are essentially doing fractional counts. Right? We talked about COVID example. If there are 100 patients with COVID, 60% of them have cough. What is the probability of cough given COVID? It's a question. 0.6. Right? And in my population, there were 1,000 people and 100 of them had COVID. What is the probability of COVID? 0.1. Okay. So what we do is simply count the number of instances that is true and divide it by the total number of instances. Right? So that's your conditional distribution, and we can estimate it. It's maximum likelihood estimation. Turns out EM is this idea where if you don't have the data that is complete, right, then what do? As we talked about, you can do imputation techniques. You can take a most probable value, you can take average, count, and then we can iterate. And so that's the idea, right? So let's take a simple example. I wanted to show this today just before the break, so so it'll kind of be a nice part to finish. So let's say you have this. So initially I only have the structure, and this is my data. Okay. So I start with an initial model. I'm basically assuming uniform distribution because everything is Boolean. I'm saying every distribution is exactly Boolean. So what I do is in the first step, I'm going to do a completion of this, where I'm going to say probability of B equals true given A equals true is half and half. That's another assumption, right? That's what I have. That's my initial distribution. So what is this going to be true? What is this value going to be? Okay, I'm going to compute the expected counts. When I'm doing the expected count, true is appeared once. Okay, true. Now because of my distribution, B being true is a half probability. So I'm going to say, well, this is with 0.5 it's going to be true, with 0.5 it's going to be false. So if I'm going to refill the data, true is now going to be one count here and a half a count from here. So that becomes 1.5. True false, I have one count from here and a half count from here. So that's 1.5. False true, again, one count from here, from this, same thing here, right? Because I start with an uniform distribution. So that's 1.5 here and 0.5 here. Get it? Now what happened is, this was my initial statement and this is my new data. So from this data I get this new data with these counts. Now with these counts I'm going to compute the probabilities. So now I'm going to say the probability of A being true, again it's 1.5 plus 1.53. That's these are the two cases where A is true, and these are the two cases where A is false. So 3 divided by, what is it, 5, because 1.5, 1.5, 1.5, 0.5, that's 0.6. So you start with a half and you've come to 0.6. B true given A is true, B is true given A is true. So A is true here, A is true here, B is true is still half and half because both of them are 1.5. So 1.5 by 3, so that's 0.5. That doesn't change, it's still the same. Whereas here it's 1.5 divided by 2, so that's 0.75. So what has happened is we started here as our original distribution. In one iteration we have converged to, not converged, we have computed this distribution. Now in the second step, use this distribution to redo this. So redo the counts. So what we do, we iterate. So here now we have this new one. This is our news distribution. We start there and complete it, and you get a different count here. Now use this count to do maximum likelihood estimation. You get this. Now you see this. Well, it's not the same as this. This is same. This is same, but this one is still not converged. Go back and redo this, and do this until you converge. Okay, so let's take our 25-minute break here. So maybe we'll come back at 11:15ish, and then we'll continue from here. Okay. Thanks. Switch this.
Sir. Hello. Sir, can you hear me? Sir?
Yeah, go ahead.
Sir, good morning.
Good morning.
Sir, to know more about this, you have mentioned a book, right? Statistical Relational Artificial
AI.
Intelligence.
Yes.
Is this a basic book so that I can start knowing
Yeah,
about?
it's very basic. It is definitely very basic. It serves more like a tutorial, so you
Okay.
can. Yeah, it is very basic. It kind of gives you all the things, and if something seems difficult to understand, it is already we have a reference, so you should be able to pull the paper out or the book out. So it has a lot of references as well in it. So it
Okay.
is a very basic book.
Okay. Okay. So what are the topics?
And if you are in an educational institution, it is also available for free. You just have to log through your educational institution. The book will be available for free.
Okay. 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 No, sir, I'm a student. So, sir, one more thing is in the
Yeah, if you're a
yesterday.
student, you should get it for free. That's my point. If you're a student, you will get it for free through your school.
Okay. Okay.
Yeah.
Sir, yesterday you talked about the probability, Bayesian nets and everything. That was fine for me. I mean, because we learned in the statistics. And today, whatever you are talking about, and yesterday you spoke about those maximum likelihood and a lot of other algorithms, right?
Yeah.
So in what are the algorithms that you uh, spoke yesterday, do we get, how can I put, do we need all those knowledge in order to learn these things? That's what
No,
you
so those are the
mentioned.
fundamentals. And again, you can read all that in the book. It's
Okay,
there in a tutorial that we have written. The
okay,
slides and the videos of these tutorials are up. So you should
okay,
be able to pick them up if you don't already have.
okay, okay, okay.
Okay.
Okay, sir.
Thank you.
Thank you, sir.
Thank you. I see a hand raised. Hello, Samir, do you have a question?
Yes, sir.
Yeah.
Hello, sir. Sir, I've also posted it in the chat. Have you, I mean, you talked a lot about these knowledge graphs in health, and I can see the strong use in especially non-communicable diseases, predicting acute attacks, for example, for stroke, for respiratory issues like COPD. Have you worked with hospitals to get these risk scores and
Yeah,
knowledge
quite a
graphs
bit.
codified?
Quite a bit, quite a bit. Actually, I work a lot with hospitals. We have a bunch of electronic health records. I've worked with cardiologists, radiologists, neuroradiologists, neurologists, oncologists, and now I'm working with pediatric surgeons, gynecologists. So we get quantifiable risk scores. So each of these diseases have their own risk scores. And then what we do is we build models that are like surrogate for those risk scores using these knowledge that I can get from them on the data that I get from both clinical studies and electronic health records. So, I mean, that's what we do. That's our lab's main focus.
And are you seeing the change in how clinicians explain for their own customers? Because we see a lot of the clinicians struggling to themselves understand how you can codify this and explain it typically to customers.
Right, right. So again, right, it depends on the clinicians themselves. There are, again, two types of clinicians, right? People who are doing out and out clinical practice, right? So that's like professors who are basically out and out teaching like 6 courses a day, and it's a busy life. So they don't have time to keep up with the research on a frequent basis. And then there are clinicians who are like doing 30 to 40% research, and then the rest of the time they have clinical service. And so depending on whom you talk to, you get a slightly different outlook. But the thing is, the problem for me is always not what they are telling the patients, but what are we telling clinicians that either validates what they already know, but you provide strong evidence for that, or nudge them in newer directions. Like yesterday I talked about this example of side effect of a drug, where there is a drug that people believed caused heart attack, but really the drug increased the blood sugar level that caused the heart attack, right? There are moments when they are getting this aha moment when they say, oh, that's awesome. There is another thing in using Alzheimer's. We were looking at a maybe I have the slide here, but they were predicting using a statistical relational learning model. We are predicting who has Alzheimer's, who does not have Alzheimer's, and the whole bunch of people in between called mildly cognitively impaired. And one thing that came out of that was the regions that we looked at, right? Parahippocampus, which is right here, is where if the brain gets soggy, the cerebral spinal fluid increases there. The brain, the parahippocampus becomes soggy, then that leads to Alzheimer's. So that came up in the top. They were like, whoa, yeah, we know that. But at the second level, the frontal gyrus came up. And they were so impressed with it because there was a debate in the community, in their community, neurologist community, whether the frontal gyrus had any impact on Alzheimer's. And the fact that we came up with it means that I was the invited speaker the next year in their annual conference. And I was able to present this result. Oh, by the way, if you get a chance, an invitation to any of these really rich conferences, you should go. They put me in a 5-star resort. Oh, the only time I've stayed that had a view of Harry Potter world. But the point I'm trying to make is that we can come up with these very nice, elegant explanations that could be a community's discussion, and we are validating it with data. So to answer your question, I think I'm more interested in what I can tell these people to get them convinced, because they have to be convinced of the model first before they can take it to the patient, right? If they just say, it's like today morning I turned on, or yesterday I was watching IPL in Tamil, which I always find funny. There was this guy who came up with a robot, and he was using that robot to make predictions. It's clear that he's just making up stuff. He had a Word document where he wrote some things, and he's pretending like the robot came up with that output. But it's what people think of robots. They can make predictions, but that's not it, right? We want to be able to quantify what we get correctly, and that is the bigger challenge, is to get a clinician accept our model, our result. And to do that, it goes back to, again, Professor Ravindran's question. how can we explain something? Like if I have a deep model, right, and I work on images, it's great because there I can just zoom in on a region that it is using, and the clinician will say what it is. Oh, that is the gyrus, that is the hippocampus, that's a paracampus. Okay, great. So we don't have to do any work, right? But on the other hand, now I use an electronic health record where I'm building this set of things together. Then I can't say that x is greater than 1.5, y is blah, 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 then they're going to get confused. You want to come up with an explanation, a meaningful semantic explanation that they can understand. That's where a common vocabulary becomes extremely important. So I think once the clinician gets convinced, then the question of can we get the thing to the general public. I hope I answered, maybe not
Yes,
exactly,
thank you.
probably approximately here.
Low uncertainty.
Yeah. All right, let's move on to parameter estimation, right? So the thing with, again, if you go back, we talked about Bayesian networks, and as I said, if you are given a logic program with probabilities, with weights, and some data, then you're going to get a giant Bayesian network, which might look like this. So you are not having a single Bayesian network. You're not having a single Bayesian network, but maybe fragments of Bayesian networks that do not look the same. But the point is, they share a common structure, right? So the common structure is there everywhere. Well, this is not here, but here. And then you have some common structure that is there in some of these fragments. What you want to do is, this is what you call as parameter trying. So you are going to say things that are looking similar should share similar parameters. So we can basically take the same maximum likelihood estimation technique that we have done and do it in the relational setting with one extra step. Identify which fragments are similar. And that can be done in a variety of ways, and that's where the research is. I can come from the knowledge graph. You start with the knowledge thing, and then the knowledge itself will tell you the similarities. That would be one way. The other way is you can actually estimate these similarities and learn from them. Okay, and this is basically is called parameter tying, and you're essentially saying that everything that is orange will have the same set of parameters. So you'll have maybe multiple blues, but there is always one green. And then here you can say there are two blues, you can aggregate them. There is one blue and one orange, one green, that is the parent, and that's easy. They share the parameters. So all you're going to do is make sure that each instance of it shares the parameters, and then exactly do your maximum likelihood estimation. Does that make sense? Yes, no? Okay, great. The same thing you can do for standard EM. And this was my very first paper that I presented 17 years back. You can take the same exact EM that we know exists and apply by making sure that the parameter tying is taken care of. So when I'm updating a count, remember I'm missing data. If there is another data point that looks similar, you use the same count there. That's it. That is all you have to do. So when you're filling this table, make sure if there are two data points that are similar, if two students are working with the same professor and one of them has a missing data, use the data to fill in the other one. And if both of them have the missing data, fill in with the same exact value for both of them. Yes, it's straightforward to do that. And of course, one way is to do aggregators. So for instance, this is actually a real problem that we worked on in 2004, I want to say, where we were predicting the population of mosquitoes. And this is a temporal data. And what they told us was the mosquito population at a day, say T, okay, depends on the number of days since the last freeze, the temperature and rainfall on each of these days. So let's say you have T1, R1, T2, R2, temperature and rainfall all the way to Tn, Rn. Okay, and then maybe you are predicting at T, the temperature. Okay. So what does it mean? If in one location maybe there are 3 days since the last freeze, the mosquito population, you take all the temperatures together, get the average temperature, get average rain, and get a distribution over the mosquito population. That is a function of the temperature, average temperature and average rainfall. Remember, average is an aggregator, which means that it is a deterministic function. If I give you the same set of numbers, you're always going to get the same output. It's an average. On the other hand, this is a conditional probability distribution. So you're only getting a stochastic function out of this. It's going to be a distribution over mosquito population given average temperature and average rainfall. Make sense? What this is missing though is there an interaction between these two? If I give you temperature and rainfall, maybe every day's temperature and rainfall has some influence that day, and we are missing it by aggregating it. So one thing that we came up with was you compute in some sense something that is not observed, which is a distribution over population for every day separately, and then you aggregate distributions to get the final distribution. It's called a combination function. The difference between these two is that here this is deterministic and then the following is a stochastic. Here both of these are stochastic. So this is a conditional probabilistic function and this is an aggregation over distributions, which is again a stochastic function. So and these were two alternatives 15 years back. But then about 13-14 years back, we showed that the stochastic plus stochastic, the combination function subsumes the first one. So whatever you can do with that, you can do with this. For mean, you can have an average combination function. If you have something like max, you have something called as a noisy max combination function, and then you have mode. Again, there is a noisy mode function that we can apply. So there is basically you can, whatever you are doing in the deterministic world, you can do it in the probabilistic world, and it's straightforward. For Markov logic network, it is actually even simpler. We'll go back to what an MLN is, just so that we remember this. I didn't realize that I have to go so back when I started doing this. Wow. Okay. So remember, you have these clauses and you have these weights. So we are in the parametric learning problem, where this knowledge is given. The weights are not given. So what we do is for every clause, when we are actually doing the learning, let me show that function. Sorry. You basically have a simple function. This is the count of the number of times a rule is satisfied. So the number of times the clause is true. Clause is same as the rule. Okay, rule I is true in the data. So you have a rule, count the number of times it's true, minus the expected number of times it is true according to the MLN. So kind of like EM, you start with some initial weights. Based on the weights, you compute the number of times you expect the clause to be true. Okay, and keep doing this repeatedly, where you are having the exact count minus the expected count. That becomes your gradient. Apply the gradient, get the new weights. The exact count is the same, so you got to do this only once. This is done once and early, and then the second term is where you are going to compute it repeatedly based on what you have and do this. This expectation typically requires a probabilistic inference, which is NP hard. It's not easy to do that. Okay, and so the computation of the expectation may require more machinery. I'm kind of again sweeping that under the rug to give you the big picture, but if you're really interested, you can look at the book or contact me and I'm happy to help. There's also the idea of generative learning and discriminative learning. This is exactly this. What I presented to you is what is called generative learning. You have the counts minus the expected number of counts for a Markov logic network. In the discriminative learning, this is where you are approximating it. Remember, you are basically saying if I have probability of x1 through xn, this is essentially probability of x1 given everything. It's called a Markov blanket. Okay, so in a Markov blanket, in a undirected model, is essentially the nodes that are directly connected to it. So you're approximating the distribution as a product of these conditional distributions. It's an approximation, but it's called pseudo likelihood. This was not published now, it was published in 1974 by Besag. Okay, and so it's a very old idea of approximating joint probabilities as product of conditional probabilities. And you can do the same thing here, and you actually get something that is much more tractable, because this requires looking at the entire model, the entire Markov network. This only requires looking at the neighbors. So it's an effective approximation. So in a graph, you are only looking at who you are related to. So if I'm saying how popular is a student based on the publication record, you are only looking at the papers that the student wrote, and not at the entire set of the data, which is what your generative learning would do. Do you get the big difference between the two of them? Yes, Abhishek. Do you have a question, Abhishek? Okay, please type it in the chat and somebody will ask.
Yes, sir. Sir, I have a question regarding this. The question is that, sir, in the expected, you are telling we are looking just at its neighbor. So it is similar to the KNNs, I can say.
I mean, if you use KNN for probabilistic inference, yeah, sure, it's very similar to that, depending on the number of neighbors you're looking at. Sure, you can think of it like that. There is an analogy there.
That part,
Yeah.
I can just constrain myself to that particular space and just see which.
That's fine. Yeah, I mean, then it's kind of like looking at the neighborhood information. You're right in that sense. Yeah.
Okay, sir.
Okay. So what we have done is, again, we have published a bunch of papers in this direction. My PhD student, who is now in Microsoft Bangalore, has published 2 or 3 papers on this topic of how to compute these effective counting using graph theory. So basically, we construct this as a graph and then use graph summary statistics in graphs to provide this information that we can use for effective learning. And what I want to really nudge you here to understand is that if you really want to do deep research in many of these problems, you don't understand one technology. Just because you understand the deep network architecture, that doesn't suffice. We want to be, has to be interdisciplinary, even inside computing. And if you go outside, for sure, it has to be interdisciplinary. Okay, and so that's what I want to highlight here. Just looking at it from a narrow lens, the research is not going to be complete at any point. But then you may ask me, why are these people just talking about only their methods? Well, they want their awards, so they want to get this method out there, and they work. Of course, the method works. That's why they do it. It's not that they're lying, but they also understand that you just don't blindly follow that. Understand that you need a combination of different methods. And this was actually one of the really good work. There is a follow-up paper that we wrote in AAAI 2019, where we took ideas from graph theory to compute these neighborhood approximations. It was a very fast counting method that was even faster than many of these databases for us to work with. So the point is that many research problems are open in this area that we can further improve. Okay. So now we will step forward a little bit and talk about structured learning, where the program is also not given. You are only given data and some knowledge. Remember, for Bayesian network, what was the knowledge? Anybody remembers? What did we start with in the structured learning of Bayesian networks? Order. Thank you. The order of the variables that allowed me to construct a Bayesian network. Remember, if you start with a different order for even the alarm network, we got a different Bayesian network. Because again, just to emphasize one more time, because somebody asked me in an email last night from the audience, you keep saying Bayesian networks are not causal models. Can you explain why? And the answer is very simple. Not every Bayesian network is causal model, because I can write out a joint distribution in multiple ways. Because if I just have something like this, right? Yes, if I have to draw this as a Bayesian network, you have this. That's the Bayesian network here. On the other hand, it is also the same as this. These two are exactly the same joint distribution, but only one of them can be causal. So not all Bayesian networks are causal, but most of the causal models can be Bayesian networks. I would say all the causal models inside the AI literature can be written as Bayesian networks, but there are some economists who are building causal models that we don't know yet how to do that correctly. But this is the simple example of why you should not look at a Bayesian network and think causal all the time. Get it? Okay. But again, right, if I give you the, so let's say this is the correct order, the second one is the correct order, or the first one is the correct order. Somebody has to give you this order, x1, x2 greater than x1. Then you will come up with this correctly. So the ordering is important. So for structure learning of logical models also, we have some domain knowledge where again it could be orders on the variables. It could be partial rules, it could be partial instances and stuff. Again, we talked about this yesterday, so I'm just going to give you a refresher here. If the data is complete, let's say we are not doing any EM, then you will start with a network. Maybe this is the network we start with, and there are three operations. You pick an edge to add, you pick an edge to delete, or you pick an edge to reverse. You do one of these three operations, and remember the scoring function again has two components. One is your log likelihood, and then your penalty. What penalty? Model complexity, right? So that's your regularization. That's for an example of that is the BIC score. Log likelihood plus the number of parameters in some sense. It's linear in the number of parameters, the penalty inside a BIC score. Okay, the same idea. So what we do is you start with an initial network, you pick an edge, maybe you delete this edge, score, see if the score between this and this, between this and this, or which one is better. If deleting is better, retain that as your new model. Or you can add an edge, or you can reverse a direction, and then you score again. The most important condition in all this is that the resulting Bayesian network has to be acyclic. So we got to keep checking for cyclicity after each of these operations is performed, and that is prohibitively expensive. So we want to make sure that there are good methods of doing it. Again, that's where theoretical computer science will meet AI. Okay, we can borrow ideas from graph literature to do these fast cycle search. Structural EM is also there. You have some initial structure, you have training data, you are doing EM because the data is partially labeled, some are not fully observable. So you have an initial structure, you have the training data, then you have compute the expected counts like how you do normally. I just showed you an example for the Bayesian network case. Use that to score again. Once you have the expected counts, you can compute the log likelihood and you can compute the model penalty. Now you have a new log likelihood. With this, you can compute the new expected counts, right? So and we can keep doing this iteratively till you converge. Does it make sense? You compute the expected counts, then you add an edge, delete an edge, blah blah blah. So that's how structural EM works for Bayesian networks. Now, in the logical case, when I'm learning pure rules and stuff, I can learn them as Firstorder logic rules. Okay, and there I have some data and some background knowledge and a language bias. And let me see if I can, if I have an example for this. I don't. Maybe I can give you an example, right? So I can say something like, so formulas. So you have examples, background knowledge, and some bias. So the example could be, you know, mother A, B. A is the mother of B, and then mother B, C, father B, C, and sorry, father A is the mother of B, B is the mother of C, D is the father of C. Okay, great. And then I can have something like that. Okay, and then let's say women B and so on. And then my background knowledge could, now I can have examples. So examples, I can say examples, positive examples is grandmother A, C. Negative examples, grandmother A is the mother of B, no, B is the mother of A, C is the mother of B. Okay, so that's the, we can say this is mother of, okay, D is the, so then this should be CD. No, DC, I was right. Sorry, just, oh God, I got confused. A is the, B is the mother of A, C is the mother of B, okay? And D is the father, C is the, D is the father of B, okay? So that's what I have. Now, I'm saying grandmother of A is C, grandmother of A is D. Okay, so this is a negative example, which means this is not true. This is the positive example, it's true. From this, I'm going to learn a rule that says grandmother of X is Y, okay, if mother of X is Z and mother of Z is Y. So what this is called, these are typically called as facts. Think of them as observations, your X in your standard feature vector representation. And then you have Y's, which are the class labels. And this is the theory that you can generate. Okay, but because you are in a logical setting, this theory search is infinite. So you will have some constraints. So you'll have some language constraints, which I'm not going into the detail. We have a bunch of tutorial on our webpage on this. So you can look at these tutorials, or if you're interested, I can talk about it later. But you have to have some constraints, otherwise you can't, this search will explode. And you can get a theory like this. Does that make sense? This is called inductive logic programming because you are inducing logical rules from some ground data. Make sense? And how do you learn it? Again, just simple greedy search. You learn a rule. First, you will start with grandmother of X, Y, if mother of XY, and then you will score. Turns out that nothing will work. So you will drop this. And then you will add something else. You will say something like mother of XZ. Some examples will be satisfied this. Because everybody has a mother, but again, some record may not be present. So you will keep building this slowly and add rules, score them. Sometimes even one rule is not enough. You have to learn like 10 rules, sometimes 100 rules, depending on your data. Make sense? Okay, so how do we do this in the probabilistic thing? The reason I showed was this is a way you can learn logical rules, but remember this is only true or false. I showed you how to learn, this is probabilistic models. And I said these relational models are essentially combination of logic plus probability, relations plus probability. So we'll put these two together. So one thing what people do was they first learned these rules using inductive logic programming and then fit the weights using some parameters learning method, maximum likelihood estimation. Works, but doesn't work very well, because if you go back here and look at how we are learning, even here, what we are doing is we are doing the structure, you'll delete an edge and then you re-estimate parameters in the inner loop. Once you re-estimate parameters, you compute the score. So the structure and parameter learning are always done together, not as two different separate steps. The initial approaches, because we had, honestly, when Professor Ravindran and I were working, the programs that we could write on our PC, we could write on today's phone. Actually, no, I'm wrong. I mean, those could have been written in phones 10 years back, in the first iPhone. That is how bad our PCs were. So in those things, when we have to learn these things, it was impossible. So people couldn't do structure learning and parameter learning together for these logical models. So out of compulsion, what people did was they learned these rules and then learned the probabilities after that. That's the best they could do. Then came methods where people started putting these two steps together, and there were a bunch of approaches. I'm not going into the detail, but I'll just give you an idea. So what happens is, here is a classic example called hypergraph lifting, where you have this data. Who is advised by whom in a university setting? Pete advises Sam. Pete is also advising Saul and Sarah. Pete teaches CS1, CS2, and Paul teaches CS2, and these are the TAs. Now what happens is, you can look at this relational database and make it a hypergraph like this, where the nodes are the constants and the edges are the relations. The hyper edges are the relations that exist. Makes sense? Do you understand this transformation? Now we are in the graph framework, right? So now what we do is we start lifting things together. So we start clustering, and essentially we get a second order idea where these are professors, these are students, these are the course, and these are TAs and teachers. So you're taking this and then start grouping things together. Group people according to what they are, group courses, group TAs, and stuff like that. Once you have this grouping, then we can start doing path finding. You start in one, traverse the path in the data graph, and then extract a rule from that traversed path. So here is an example. I can start from here, advice, and go to teachers. And from advice, I could go to teach and go to a TA. Okay, and I can start writing rules based on that. Right, so I can basically say advices, I can get teachers, and then I can get multiple rules, and then I can create a class for these people where these students are advised by these professors, and these professors are teaching these courses. There are students who TA the course. So now I can basically write a rule that says, if P advises a student and P teaches a course, and if the student is the TA for that course, you can extract that out, and that becomes a class. Advices, PS, teachers, and TS. So all we are doing is essentially taking this database, constructing into a hypergraph, and walk in the space of hypergraph and get the rules out from that. And remember, this rule need not be satisfied by all the examples, and that is where weights come in. So you extract a rule, you learn a weight, and then score the model and see if you want to change that rule, and we can go from there, right? But again, now we can do more smarter things. We don't stop with here. We can say, well, if there is a advisors, how about we add not teach, not TA, or teachers and not TA? We'll come now start introducing all these logical combinations on top of it, and we can kind of build this set of clauses. Each time you learn a clause, you score it. Get it? I mean, I see a lot of you nodding your head, and of course some of you don't care, but that's okay. But most of you seem to be nodding, and if you don't get it, I'm happy to explain again. Which part? Like, do you get this part? This part is clear? From this, do you understand me writing this rule out? Okay. Now remember, we are in a logical setting. There are three things: and, or, sorry, and, or, and not. So what we do is we try to change this and to an or. We can introduce a negation for every predicate. So that's not of something. And so we can basically build these combinations of clauses that we can search over and score each of them with the data. Again, right, you can take this vanilla approach as it is. There is a lot of research on how we can score this faster, how we can construct these combinations faster, what do these combinations even mean? And so those things we can, that's where these open problems still lie. Okay. So you can actually get a rule that says something like this. One of the rules that we can extract is advices PS if teaches PC and TASC. This is basically saying a student is advised by a professor if the professor teaches a course and a student is a TA for that course. And then you can learn a weight. It's actually a pretty high weight. I think we had something like 1.9 or something. It's again exponential. So 1.9 is e raised to 1.9 times the number of counts. So it's actually a very high value in the ground network. And then you can actually have another rule that could say something like advices PS. You can have rules that say something like publication P, we'll call it a paper, and publication, or maybe we can call it authors PA, authors SPA. When they co-author a publication, they are, a student is advised by a professor. Turns out this is slightly even higher. Okay, and actually the third rule could be advice PS, again authors PA and authors SPA. Now we can even type it saying Professor P and student S. This will have even a higher weight, because now we are actually grounding, because this could be two students. In this rule, there is nothing that says S is a student and P is a professor. It could be that S is also a professor and P is also a professor, or S is also a student and P is also a student. So now you can see that the weight here is higher than the weight here. Again, I'm made up, everything is made up. But I hope you're getting what I mean here, right? So this is what the rule means. See, if you want something like this, you have to do, this is called discriminative learning, like a classic machine learning sense. I have positive, this is my positive examples, positive and negative examples, and then I can learn from it. The general rule is what is called as a generative learning, where I'm kind of like learning a Bayesian network, where you learn a network and you can always instantiate something as your evidence and query something else. Yes, with me? Okay, are there any questions from the online group? Because I'm going to go to the last part of this tutorial, kind of showing what we have done. Mhm. You could, yeah, you're right. You could do that, but you could also think of learning all 20 rules from the data. So it could be both. You're right. Like I might learn 10 rules and then manipulate these 10 rules to generate more rules, or I could be learning all those 20 rules from data. I mean, I'm not saying I'm doing one versus the other. Both could happen. Okay. Yeah, there was a hand I thought in the online. Is there a question?
Sir,
Yeah.
when we are learning these weights for these rules under different conditions, like you in the last slide you showed, is it like finding the weights for the conditional distribution?
Yeah, exactly. That's what it is. It is the learning each weight. It's not for the conditional distribution. Each weight that represents the conditional distribution.
Okay.
Each weight models the conditional distribution.
You don't
Each weight gives
enumerate
you.
and find all weight, all possible.
No, you can't do that enumeration, because that's still infinity. So you have to search, or you're talking about numeric search. You can't just enumerate the weights, because these are real weights. By the way, the weights of an MLN goes from minus infinity to plus infinity. Minus infinity means this rule is never true in the world. Plus infinity means it's always true in the world. You can't enumerate that. So you just can't enumerate it. Instead, you have to have some numeric methods to search over potential weight.
Isn't each clause each clause is like a condition? It's like
Yeah,
a
each
conditional
class
probability
defines.
distribution, so that we can enumerate.
Each class gives you the structure of the distribution, not the parameters. Each class gives you the structure of the distribution. It tells you which two attributes are related. What each class does not give you is the weights. So I understand I guess the blind spot here. Each class is not giving you the distribution itself. It gives you the form of the distribution, the structure of the distribution. The actual parameters of the distribution have to be estimated from the data.
Okay.
Okay, that's a great question. Thank you. Yeah, it does make it clear. So thank you. Any other question, or can I move on and wrap up in the next 20 minutes? Okay, so I'll talk about this idea, right? The idea is very simple. Remember, I talked about parametric versus non-parametric in the beginning of this class when I talked about SRL method. So one thing that we had an idea was these SRL models always are finding a finite set of parameters, which means I have a rule, I have a parameter. I have a finite set of rules that I'm learning, like you just pointed out. Even with that combination, it's a finite set. And for that finite set, I'm getting a parameter. How about we do this in the non-parametric way, where people have learned classic machine learning models where they just keep adding to the model as you get more data. So one way we thought we will do is drop the finite model assumption, and we will go for something like non-parametric learning. So if you think of these learning characteristics, it's thanks to Tushar Kot for his this slide. You have expert's time. How much time does an expert need to do? If I'm giving you the full model, where I'm giving you the model of the network and the parameters, the expert has to do all the work. There is no learning. At the other extreme is, or if there is parameter learning, then the expert gives you the structure of the model and the data, and you're fitting the conditional distributions. So there is some learning there, but there is also a lot of work by the expert. If you do structured learning, you're just given the data and you have to learn the full model from it. Now the goal for my student Tushar Kot, his thesis was, can we somehow bring this closer to the parameter learning in terms of the learning time, not in terms of experts' work. So we were trying to bring this closer, and the way we did it was using the machinery of functional gradient boosting. Gradient boosting, how many of you know XGBoost? Half of you, right? Gradient boosting that we are doing is a richer form of XGBoost. Okay, so I'll explain what XGBoost is. If you already know, stay with me, because this explanation might be slightly different for what you know. The idea is very simple. You take the current model, whatever that model is. Remember, when we did the structure search and stuff, or even parameter learning, we started with some initial assumptions. In the parameter learning, it was uniform distribution. In the structure learning, it was some random structure that we start with. Like this, this initial model could be it could be anything. It could be just some initial uniform distribution. You make predictions on the data. Compute the difference between the data and the predictions. Right here, that becomes a gradient. So let's think of a simple example. I want to say, who is going to become a millionaire? I've always used heart attack as example. I find it depressive during COVID time. So we'll move to something more fun. Who will become a millionaire? Okay. I don't know. I'm just going to pick Nishant here, right? So he's doing his schooling at IIT. He's finishing his masters and whatever, and he's going to go join a company. So he's going to become a millionaire. On the stage is a professor who by definition cannot be a millionaire. So he is the positive example, I am the negative example. Now my model initially will learn something from the data. That's my initial model. Initial model, because initial model is, let's say, prior, it's just half. So it says with 0.5 probability he'll be a millionaire, 0.5 probability I'll be a millionaire. According to the data, he is a millionaire. So his weight is 1, because the probability of him being a millionaire is 1 in the data, right? You are a millionaire. So it's 1 minus 0.5. 0.5 is his weight. I, on the other hand, is a professor. So I can never be a millionaire. So my weight is 0 minus 0.5. 0 should have been the original label, but you are giving me 0.5. I am negative 0.5. Every positive example will have a positive gradient, because it's 1 minus, and the probability, remember, a probability is always less than or equal to 0, sorry, less than or equal to 1, between 0 and 1. So your gradient, positive examples gradient will always be positive, negative examples gradient will always be negative. So he has a plus 0.5, I am a minus 0.5. We learn a model, which could be a tree that I showed you in the beginning. Remember the heart attack tree? You are learning a tree like that. Add that tree to the model. Now the new model predicts him to be a millionaire with 0.8 probability. it predicts me to be a millionaire with say 0.26 probability. So his weight is now 0.2, 1 minus 0.8 minus negative 0.26. So what happens now is that my new model is not going for the original 1, 0 or the 0.5, 0.5, but it's the new thing that it is fitting. His gradient of 0.2 and my gradient of my negative 0.26. So it's trying to fit gradients that are just computed from the data. Once that computation is done, then you're only fitting for you for a 0.2 and me for a negative 0.26. So it's not trying to fill in the full data, but it is just filling the gap. And you're learning a new tree. And you keep going until you converge, where either he goes down to 1 and I go down to 0, or we define, look, I don't want to overfit, so not too much of a model complexity. So what do these models look like? These are short trees, short rules, not long rules. The key when you're learning these is that these intermediate models need to be very short. If these intermediate models are very long, you will easily overfit. So you don't want to let a tree grow fully. It should be typically a tree of depth 2 at most, 3 sometimes. So what we do is we learn these short trees and we keep going until we converge. Now the cool thing is, if you go back to my tree, remember we had a tree like this, and at the end of the tree we always had a number. That number is the number that is going to get you the negative 0.2 and me the negative 0.26. So it will be it's a regression number. So one advantage here is, unlike standard Bayesian networks where I learn a network and then I fit the parameter and then I score it, here there is the fitting of the parameter comes while I am learning the tree, because at the leaves I have numbers. So instead of doing structure learning and parameter learning as 2 different steps, we put them together and we learn them. Does it make sense? So this is what we developed, and this is what we are known for the last, what, for 10, 12 years. Yes, does that make sense? Anybody has any questions? The form of the trees I kind of gave you in the first slide. So we can learn relational dependency networks, and why is it justified? Because again, if I'm saying the probability of an example being true conditioned on the parents, if I write a sigmoid function, so in normal gradient descent, these are called theta, and you will take the gradient of the log likelihood with respect to this theta. Here I'm going to take the gradient with respect to the function psi, and when you take it with respect to the function, then instead of, remember, if in the log, if in the original log likelihood yesterday that we did, we said we take the probability of the first example times the probability of the second example times the probability of the third example, then take the log, which led to log sum of the logs instead of the log of the products. Now you get sum of logs, and we have to do it. Here we compute the gradient for each example separately. So it's actually faster to do this than the other method, because we just get the gradient separately and work with the gradient faster. So, and the gradient comes down to this nice expression, which is, what is it going to be true in the example? 1 if it's a positive example, 0 if it's a negative example, minus the probability of being true according to the model. So it's a very simple expression in the end, and it works beautifully. That's why when people tell me that they have this nice tabular data set and they are doing deep learning, I go like this, because this is the method. XGBoost is the method which works for tabular data. Be it any Kaggle competition, anything, this works great. So if you have tabular data, please try this first before you try any deep architecture. There is also, if you're really interested, there is an equivalence between deep network and this. Actually, the training procedure, there is a direct equivalent between XGBoost and how you train a deep architecture. I mean, that's slightly technical, I don't want to go there today, but it can be proved. Okay. And so I always suggest try XGBoost before you try a deep network if you have non-imaging, maybe NLP data. Okay, so that's a pro tip, if you can say that. Okay, now again, right, if you look at this corner, just here you can say that x1 is a positive example, while x2 and x3 are negative examples, because remember, positive examples will always have a positive gradient, negative examples will always have a negative gradient, and the rules are going to be very short like this. Is there an eraser here? If I can erase this part, you can see this clearly. The rules are very short, and at the leaves you have the parameter values. Does that make sense? We have again learned Markov logic networks exactly like this, and we can learn Markov logic networks, and it is again boiling down to the number of times you are saying the example is true minus the number of times the example is false. Sorry, the clause is true minus the clause is false. We can do this for every example, and you can actually compute this. Again, it's an approximation, it works great, it's the state of the art learning. And you can actually, what we do is we learn trees even for Markov logic networks and convert each path from root to leaf as a rule. So you learn trees and converted them into a weighted logic rules, and that works also great. And we have a similar algorithm for logistic regression, and we can learn everything. And I'm going to skip this part, but I also wanted to say that we have done temporal models, right? So again, right, hidden Markov models, somebody asked me in the morning, and they can be learned very easily because it's just a very simplistic model compared to what we have. But any of these hidden Markov model and everything, the inherent assumption is what is called Markovian, which is the future is independent of the past given the present. So if I know today, that's all I need to do to predict tomorrow. What happens? That's first order Markovian, by the way. So when we say Markovian, it's typically first order Markovian unless explicitly specified. But then the data on the, if you look at it, comes at a irregular intervals, right? So blood pressure, maybe you can monitor it. EMI, you can monitor it. Exercise, maybe because of all these gadgets, we monitor more often. But heart attack, we don't monitor that often. Only when you know, you get it, right? And the more depressing example is all of us die at some time. The longer you wait, the higher is the probability of dying. And that can be captured by an exponential distribution. And they basically build what is called continuous time, where you have a temporal dependency. You have cardiovascular disease that depends on blood pressure, cholesterol, BMI, diabetes, whatever treatments we have, and each of them have their own things that they depend on. So it's a Bayesian network, but over time. And what we have shown is that you can actually learn. I'm going again skipping all the details because I don't want to focus on the detail here, but give you the big picture. We can learn this using the gradient boosting method, and you can actually show that we can we not only learn, but it's a convex problem. So we learn to the global optimum. We get the best structure possible for these problems. It's in AAA 2016. Okay, and of course we've got some excellent results. We have done this with hidden data. I'm not going into the detail, but it's the same EM algorithm. Just take EM algorithm, put it in gradient boosting, and we've got some results on this. If you're interested, we can do this. It's not under review anymore. We can do this for reinforcement learning in the presence of objects and relations, and that works. So I just wanted to give you the idea of things that we can do, and the different types of distributions that we can learn with. We have worked with multinomial, but the form of the gradient is going to be different. So in multinomials and exponentials, the gradient is additive, but in Poisson, the gradient is multiplicative. So the gradient form can be different, but we can do this on many domains. And as I said, we have done this on many applications. That's our claim to fame. Okay, with that, I think I'm going to spend the last 10 minutes motivating some other research areas. Of course, we also scaled this using scaled boosting using databases, where in the search process and counting were essentially reformulated using databases. And this is what I'm trying to explain. I hope you are getting the one message that I'm giving correctly, which is that I'm not sitting here and saying the Bayesian network methods and the probabilistic graphical models and everything has to be just done in one way. We used at one point graph databases to accelerate counting. Here we used relational databases to accelerate counting. We got the best paper award a few years back for this, actually very fast in many problems. Again, everything that we do is available online, and all the code is available publicly. So if you want to reach out to me, and I'm happy to help. Okay. I think I've lost, maybe I'll finish in like 5 to 10 minutes by just talking about not just human. Yeah, but they're tired, so I'll finish in about 10 minutes. There was a question about what can we assume from humans, and I'm saying that if you talk to a doctor, I think it goes back to the question, I think Samir asked it, about how do we communicate with the doctors. Okay, if you work with the domain expert and you tell the domain expert, you just give me the data, I'll give you the model, they're going to throw you out. Why? Because they have worked on this problem for themselves for decades, their community for centuries. You just don't want to throw that out. We want to be able to take the data, right? So what I want to do is basically that go from looking at the structure learning methods where only the examples are given and human is just a mere labeler, versus weight learning where, or parametric learning, where the human gives you the model and then you fit the data. But to me, the sweet spot is somewhere in the between. Okay, and we want to explore this direction, and this is what we call as advice giving. Again, it's not a term that I came up with. Chavlik was working on it in early 90s, but one of the most seminal papers, really, if you want to read, 1965, John McCarthy's paper on advice taking systems. It's beautiful. It was like a visionary paper. Of course, it didn't have a solution, but the things that you can learn from. So this term of advice taking has been there for now nearly 60 years. Okay, it's not like we are, again, right, many of these things we are presenting as if it's new, but it's not. It's been existing for a long time, and we're just making them better, right? And let me just talk about what these advices are. Some of these are things like monotonicities, things, for instance, higher BMI increases the risk of heart attack. Okay, more expensive 19th over increases the chance of losing in an IPL game or any T20 game. On that note, did you notice that there is a new trend in the T20 games? Back when only one-dayers were played, that 50th over was always bowled by the best bowler. Now the 20th is not bowled by the best bowler. The 19th is the bowler that is bowled by the best bowler, particularly in a chase. Because you want to give the 20th bowler as much cushion as possible. Okay, but this is an advice that people who follow the game very well can give, and your learning algorithm should be able to use that information. If you ignore that information and just let the data tell you, because of the fact that the search is so huge, you will lose it. A more important example is precision versus recall, sensitivity versus specificity. It's something that people talk about all the time. If I'm building a model to predict diseases, you want to reduce the number of false negatives. Because think about COVID. If you give a lot of false negative tests, this pandemic is never going to end. Okay, you identify the people, put them on treatment, whether isolation or not, that's a different point, but get these treatments in, we can get rid of this thing quickly. Specifically in Ebola, even a single false negative can actually cause a huge pandemic. So you want to be able to make sure that your recall is high. Every morning I get an email from LinkedIn saying there is a position in Indiana University open. I resigned from Indiana University 5 years back. And the position that they want me to apply is a postdoc position on a project for which I was a PI. Why? Because they are not maximizing precision, they are trying to maximize recall. They are trying to get every position that is relevant to me there. So if you just measure accuracy on many of these models, you're going to fail. It's not the accuracy. Some models need high precision, some models need higher recall. You have to understand the problem deeply and figure out which works where. Get it? So that's the second thing. The last one is preferences. I mean, there maybe third one is preferences, where you can say, I prefer that if these things happen, this be the result. Okay, so I prefer that you stop at stop signs if it is safe to do so. I prefer you slow down at curves, unless you are chased by somebody. You want to slow down, right? So these are preferences statements that you can bring as domain knowledge. You can say, I prefer that everyone is treated fairly. On the other hand, if you want to focus on a particular subpopulation and make sure they get preferential treatment, you should be able to say we should focus on this subpopulation because they need preferential treatment to attain parity, and we need to be able to say that into the learning system. You've heard of this term fairness in AI a lot. That's a preferential statement. The last one is privileged information. It's kind of like your exams. As a teacher, many of us give you hints at how to solve problems, but at the exam time you cannot use those hints exactly, but you use those hints to guide you to a better solution. A better example would be in this is actually a real problem that we work on, where we have these are MRI images, and this is our electronic health record data, but then in addition we also get some cognitive testing scores, and we put people on smart homes and smart devices. But this is a clinical study. In clinical study, I get periodic cognitive test scores and I get the smart devices data. But once the model is built and I'm going to deploy it in the hospital, the physician only sees the electronic health record and the fMRI. So while building a model, this part should not be used in the model. But when I have two competing models, these extra is going to choose between the two models. That's why it's called privileged information. It's there during training, but not during testing or deployment. Vapnik was the one who came up with this idea. We built on it, and we can actually do this again as trees. We solved this on a whole bunch of problems and got some good results. The only difference is, I think I said this in the first class, I said you have the log likelihood plus a model complexity, right? I said this. Now you add this to a advice complexity, advice penalty. So essentially use the advice as a regularization. So what we do is, instead of just using the data and predictions, you also take the advice and say, okay, have some advice on it, and you say, well, yeah, this is a young student, so the chance of getting to a millionaire is very high, and you use that information and add it to the model and do the same thing over and over again. So basically this was our original term, I minus p, whether it's true in the data minus probability of being true in the model. Now we have a advice penalty, which is saying how many times is an advice satisfied versus how many times is it violated. Okay, and we can do this again in the concept of sequential decision making, reinforcement learning, planning, inverse reinforcement learning, and so on. But if you have good advice, we actually solved a problem in Los Alamos National Lab, and we solved their problem. They had these images where they had to look at these microscopic images and identify some segments, and we were able to solve it with 99.1% accuracy with a bunch of rules that human used. We used the rules and then the data, and we were able to solve. It's a system that they have now for the microscopic images. I'm going to skip all this, and I'm just going to say, when it comes to humans, not all advice are equal. Humans are great at stating the obvious. So whatever human says, half of the time it's true in the data. The real value for these advice are rules that are not there in the data. So advice, essentially you can think of them as polygons, okay, in space. So this black region says that everything inside this black triangle should be black. Everything inside this blue, the rectangle should be blue. But then not all advice are equal, okay. So this is absolutely useless, because the data here and here will always make sure that this region is black. And similarly, if I have something here that looks like this, it's useless. Whereas this and this is very useful. So the question is, how can we make a system get these information? So what we have done recently is saying that we don't need the advice to be given before learning, but as the system is exploring, it should ask specific questions. Hey, I don't understand this example. It's very confusing. I really thought this person is not going to have diabetes, but this person has diabetes. Can you explain why? And the person could say, yeah, because whatever you are doing were risk factors for type 2 diabetes, but his genetic sequence points to type 1. Oh, thank you. And I fix it. So it's like you sitting there, and if I tell you, ask all your questions to me before, I start my lecture. It makes no sense. As I'm talking and you are not clear on some concepts, you put your hand up and you ask a question. We want the system to be able to do that. In some sense, emulate a real teacher-student interaction, where the teacher is the domain expert, the system is the student, and we are able to do that as well. So I'm going to again close with not going to details of all this too much, but I just wanted to say that we have even built NLP interfaces. So the questions can be asked in English. You take these logical statements. That's one of advantage of writing something in logic. Goes back to again Professor Ravindra's question. We decide on some of these symbols upfront, and we can ask questions about these. Okay. So remember that if I want to do artificial intelligence, it's more than a single table. If there is one thing that you should take from today's class, is that it's not a single table. You can have databases, you can have graphs, you can have everything, right? And then we should be able to learn from everything. We want to have symmetries, and we can exploit those symmetries in both learning and inference. Sequential models should be not very simple. We should be able to learn with complex models, and of course, use humans as an ally. And there's a lot of work to be done in this area. Okay. So we are interested in doing kind of like scaling this up to very large databases. So we are working with a bunch of people on that. We are also interested in learning from multiple experts. I don't like the idea of crowd of experts, because to me crowd is never expert. Crowd is crowd. You can say wisdom of the crowd, that makes sense, but crowd of experts is kind of an oxymoron for me. But we also want to have some efficient learning and hybrid models here. And I have a dream, right? And all of us have a dream, and that is learning in the presence of partial information, where the information is partial, but it is a rich, tough domain, and I want to be able to go from there and learn in the presence of this. With that, I'm done. So if you have questions, we can talk. Otherwise, thank you for attending the workshop. Yes, questions online too. Yeah, Dr. Lakshmi, you have a question? Is there a question from Dr. Lakshmi? You raise your hand. Okay, meanwhile, anybody here, any questions?
Hello.
Yeah. 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 Most of these
Hello.
are.
Good afternoon. Sir, I'm from the beginner. I don't know the machine learning, deep learning, or then the AI. So where will start doing work? Then it will be benefit for me.
Sorry, what was the last question?
Then what is the where will you start? That will be benefit, and that will be helpful.
Yeah, so
for
start with
doing
a
research.
good AI textbook. Start with a good AI textbook, and I suggest
Textbook.
Russell and Norvig. Russell and Norvig. It's a very
Is
good
it
AI
openly
textbook.
available?
I don't know, but it's not that expensive here in India. It's very expensive there, but it's not very expensive here.
Sir, name again, book name?
Stuart Russell and Peter Norvig, Artificial Intelligence, A Modern Approach.
Okay.
That's a good book to
Because
start.
there are so many things without knowing at the now what are going, it is difficult to achieve. So
Yeah,
I think
so
that
that book gives you the foundations if you want to really
okay.
dive deep. But again, there are some there are some popular AI books that one could read. There is a Book of Why by Idia Paul. There are a whole bunch of other books. Again, Master Algorithm by Pedro. Michael Kearns has a book. Gary Marcus and Ernest Davis has a book. So there are a whole bunch of popular AI books, but they are not technical. So if you want to really read technical, I suggest start with the Russell and Norvig, and I think that's a good book to start. Norvig, Norvig, Norvig. Yeah.
Okay. Thank you, sir. Thank you, sir.
Thank you. Yeah.
For valuable.
Any other questions? Maybe I stopped sharing because there was a bunch of questions in chat. advice taking paper, detail, author name and year. It's there on my paper web page. Philip Odom, I forgot the year, 2017 maybe, 2016. Philip Odom and I. It's there in my and my email. You can basically get it sriram.natarajan@utdallas.edu. But you search on Google, you should be able to find that. Can we use this graphical model for fraud detection? Absolutely yes. There are a couple of companies where my students are working now, and they use this model for fraud detection, anomaly detection, and other problems. And we also work with a group that does fraud detection from a security perspective. And lastly, structured learning path after this workshop. There is a whole bunch of work on structured learning in probabilistic graphical models. I suggest you look at that. There is a tractable probabilistic model workshop that happens every year. There is also workshops on statistical relational AI that is happening even in ICHCAI this year. ICHCAI is a conference, International Joint Conference in AI. They have a star AI workshop. So you should be able to follow that. How can this be implemented in Gaussian processes? Again, I kind of skimmed it. There is a paper by Christian Kösting on relational Gaussian processes, and you can actually see that essentially you can define these Gaussian processes using some of these clauses. So yes, and that is that can be one way to do it. If you're interested, send me an email. I can point you to that literature as well. I'm bioenergy again, right? Depends on the problem. As long as you have a problem where you can have some questions, where you can have some rules and data, it doesn't matter what the problem is. I can have some domain expert guide the model. We should be able to learn these. Yeah, I understand the overwhelming nature of all this, which is why you got to start somewhere. And I suggest starting from the Russell and Norvig book. I think chapter 12 is on uncertainty. Chapter 6 is on logic. Once you get these two done, then you can start reading our book, because you will get the fundamentals. Then you can start reading our book. Yeah, you got to take slow steps to get there, which is why I keep focus there. My website, again, search for Sriraam Natarajan. Sriraam is 2 A's, SRIRAAM, Natarajan. You should be able to get. Time series forecasting. Time series, is there a book that we can recommend on time series modeling? The AI books all have time series in them towards the end. So, but I don't have a specific recommendation for time series forecasting. Sharing the slides, I am absolutely okay with it. I'll work with RBCDSAI to share the slides. That's not a problem. Okay, in that case we are done. Thank you. I mean, I have left the slides here, so I mean they can upload it if you want somewhere, or